There is something quietly remarkable about the way winter mornings can hold their stillness, as if the world itself pauses, and on one such morning, a golden mirror began its long journey toward the cold darkness between Earth and Sun. It was Christmas Day in 2021, and while families across the globe exchanged gifts and gathered in warmth, a rocket lifted off from the northeastern coast of South America, carrying within its protective fairing the most ambitious astronomical instrument humanity had ever constructed. The James Webb Space Telescope had been decades in the making, delayed and redesigned countless times, until finally it rose on a pillar of flame toward the silent frontier that had been waiting for its arrival. In the weeks that followed, the world would watch with held breath as this extraordinary machine unfolded itself in the vacuum of space, preparing to reveal a universe far more detailed and ancient than anything our previous instruments could perceive. Tonight, we are going to spend some time exploring the remarkable discoveries that Webb has already delivered to us. Traveling from the earliest galaxies at the edge of observable space to the atmospheric chemistry of worlds orbiting distant stars. We will examine the stellar nurseries where new suns are being born, hidden behind veils of cosmic dust that only infrared light can penetrate. And we will revisit familiar objects like the pillars of creation with fresh clarity that transforms our understanding. There'll be dying stars casting off their outer layers in beautiful expanding shells. And there will be galaxies so ancient that their light departed before Earth itself existed, each observation contributing to a growing tapestry of knowledge about the cosmos we inhabit. This is a journey through some of the most significant astronomical revelations of our era, presented gently so that the wonder of these discoveries can accompany you through the quiet hours ahead. Before we begin, I would appreciate a small kindness from you tonight. Just a moment to share in the comments where you are listening from in the world. If these calm explorations of science have helped you find some peaceful rest before, perhaps consider subscribing so that you can return to these quiet journeys whenever you need them. Now, let us turn our attention to that December morning when everything began, and follow the Webb telescope on its remarkable voyage to the edge of night. The Ariane 5 rocket that carried Webb into space was a European contribution to an international collaboration spanning decades, and its performance on that Christmas launch was so precise that it extended the telescope's operational lifespan beyond original expectations. The fuel that Webb carried was intended for course corrections and orbital adjustments over its planned 10-year mission, but the rocket's accuracy meant less fuel was needed, giving the observatory additional years of potential operation. Engineers and mission planners had prepared for this moment through countless simulations and rehearsals, knowing that even a minor malfunction during launch could end the mission before it truly began its scientific work. The rocket performed flawlessly, separating from its precious cargo about 27 minutes after liftoff, and Webb began its month-long coast toward a gravitational balance point called Lagrange 2, nearly 1 million miles from Earth. Lagrange 2, often abbreviated as L2, is a remarkable location in space where the gravitational pull of the Sun and Earth combine with orbital mechanics, creating a stable region where a spacecraft can maintain its position relative to our planet with minimal fuel expenditure. This location keeps Webb's sunshield perpetually oriented between the telescope and the 3 brightest heat sources in our vicinity, blocking light and thermal radiation from the Sun, Earth, and Moon simultaneously. The telescope's infrared detectors must operate at temperatures far below freezing, approaching -200 degrees Celsius, because any warmth would create thermal noise that would overwhelm the faint signals from distant galaxies. At L2, protected by its tennis court-sized sunshield, Webb can maintain these frigid conditions indefinitely, allowing its sensitive instruments to detect infrared photons that have traveled for billions of years across the expanding universe. The journey to L2 took approximately 30 days, and during this transit, the telescope underwent a series of carefully choreographed deployments, unfolding structures that had been compressed to fit within the rocket's payload fairing. The sunshield deployed first, stretching out in 5 thin layers of a material called Captain, each layer coated with reflective aluminum to bounce solar radiation away from the telescope's sensitive optics. This deployment alone involved hundreds of release mechanisms, pulleys, and cables, any one of which could have failed and ended the mission if not perfectly executed. Engineers on Earth monitored telemetry anxiously as each step completed successfully, celebrating quietly with each milestone achieved, until the sunshield was fully extended and the telescope began its thermal descent toward operating temperature. Next came the deployment of the secondary mirror, a smaller reflective surface held at the end of 3 long struts, positioned to catch light reflected from the primary mirror and direct it into the scientific instruments. The primary mirror itself, that iconic golden hexagonal arrangement, had been launched with its 18 segments folded, and these wings now swung into position to form a single continuous light-collecting surface over 6 meters in diameter. Each segment was coated with a microscopically thin layer of gold, chosen for its excellent reflectivity in infrared wavelengths, giving the telescope its distinctive golden appearance that has become an emblem of modern astronomy. The alignment of these segments would take months of painstaking adjustment, using tiny actuators to position each mirror within nanometers of its ideal location. But even in these early days, the fundamental architecture of the telescope was taking shape exactly as designed. By late January 2022, Webb had arrived at L2 and begun the slow process of cooling to operational temperature, while ground teams initiated the careful calibration of its instruments and optical systems. The telescope carried 4 primary scientific instruments, each designed to observe the universe in different ways, including cameras and spectrographs optimized for various regions of the infrared spectrum. The near-infrared camera, or NIRCam, would capture the high-resolution images that would soon astonish the world, while the near-infrared spectrograph could analyze the chemical composition of distant objects by spreading their light into component wavelengths. The mid-infrared instrument, known as MIRI, required even colder temperatures and could see wavelengths invisible to the other detectors, opening windows to thermal emissions from dust clouds and cool planetary atmospheres. The months between arrival and first scientific images were filled with meticulous preparation, as each mirror segment was adjusted and the instruments were tested against known celestial targets to verify their performance. Engineers used stars of known brightness and position to calibrate the pointing accuracy of the telescope, ensuring that when scientists requested observations, the telescope would aim at precisely the correct location in the sky. The 18 hexagonal mirror segments, each about the size of a coffee table, were aligned so precisely that together they functioned as a single, monolithic surface capable of resolution impossible with any previous space telescope. Hubble, the beloved predecessor that had revolutionized astronomy for 3 decades, had a mirror 2.4 meters in diameter, while Webb's 605-meter primary could collect over 6 times more light and see far deeper into the infrared universe. Infrared astronomy is essential for studying the distant universe because of a phenomenon called cosmological redshift, which stretches the light from ancient galaxies into longer wavelengths as it travels through expanding space. Light that departed a young galaxy as visible or even ultraviolet radiation has been traveling for billions of years, and during that immense journey, the universe itself has expanded and stretched the wavelengths of those photons. By the time this ancient light reaches our detectors, it has shifted into the infrared portion of the spectrum, making it invisible to telescopes like Hubble that primarily observe optical wavelengths. Webb was designed specifically to capture this stretched light, gathering the oldest photons in the observable universe and translating their faint infrared glow into images and data that reveal the cosmos as it appeared in its youth. But Webb's infrared vision serves another crucial purpose beyond detecting cosmologically redshifted light from the early universe. And that purpose involves penetrating the dense clouds of dust that obscure many regions of space from optical view. Visible light scatters when it encounters interstellar dust grains, blocking our view of whatever lies behind the cloud, while infrared light passes through these dusty veils, largely unimpeded due to its longer wavelength. This means Webb can peer into the hearts of stellar nurseries where new stars are forming, revealing protostellar objects and processes that remain completely hidden from telescopes working in visible light. It can study the centers of galaxies, the formation of planetary systems, and countless other phenomena, all occurring behind curtains of dust that would otherwise render them invisible to our instruments. The team preparing Webb for its first observations understood that the initial images would carry significance far beyond their scientific content, establishing the telescope's capabilities in the public imagination and justifying decades of investment and effort. They selected targets carefully to showcase Webb's range of abilities while delivering genuine scientific value, including deep field observations, stellar nurseries, dying stars, and planets in our own solar system. Each target was chosen because it could demonstrate a different aspect of the telescope's capabilities, from resolution to sensitivity to spectroscopic precision across multiple instruments. The world would soon see what infrared eyes trained on the cosmos could reveal, and the astronomical community prepared for revelations that would exceed even their considerable expectations. As summer approached in 2022, Webb completed its commissioning phase and prepared for the release of its first full-color images, a moment that would mark the official beginning of its scientific mission and introduce its capabilities to the world. The telescope had performed beyond specifications in virtually every measurable way, achieving sharper focus and higher sensitivity than even the most optimistic pre-launch projections had predicted. Its mirror alignment was nearly perfect, its instruments were operating flawlessly, and its orbit at L2 was stable, providing ideal conditions for observations that would soon rewrite chapters of our astronomical textbooks. Everything was ready, and the universe lay open before this remarkable machine. On July 11, 2022, a preview of the first Webb image was released by the President of the United States, a tradition that acknowledged the telescope's significance as a triumph of human ingenuity and international cooperation. The image showed a galaxy cluster called SMACS 0723, rendered in unprecedented detail with thousands of distant galaxies visible behind it, their light bent and magnified by the cluster's immense gravitational field. Astronomers and the general public alike stared at this image with a mixture of wonder and emotional response, recognizing that they were seeing deeper into space and further back in time than any previous observation had allowed. The following day brought additional images and data, each one revealing new capabilities and new discoveries, establishing Webb as the most powerful observatory ever placed in space. The golden mirror that had launched on a winter morning had finally opened its eye upon the universe, and what it saw would transform our understanding of cosmic history from its earliest moments to the present day. In the parts that follow, we will explore these discoveries together, taking our time with each revelation, allowing the science to unfold at a pace suited to these quiet hours. We will travel to the edge of the observable universe and back to our own solar system, examining what Webb has taught us about galaxies, stars, planets, and the vast structures that connect them. For now, rest with the knowledge that somewhere beyond the moon, a patient machine keeps its vigil, and its golden eye continues gathering light that will illuminate our understanding for generations to come. Now we will examine that first deep field image more closely, exploring what it revealed about gravitational lensing and the thousands of ancient galaxies hidden within a seemingly empty patch of sky. The image that appeared on screens around the world on that July evening in 2022 seemed almost impossible in its density, containing more galaxies than most people had ever seen in a single astronomical photograph. This was SMACS 0723, a galaxy cluster located approximately 4.6 billion light-years from Earth, serving as a massive gravitational lens that bent and magnified light from even more distant objects behind it. The exposure time for this image was only 12.5 hours, a relatively brief observation by deep field standards. Yet it revealed thousands of galaxies with a clarity that surpassed anything achieved by Hubble over decades of operation. Each smear of light, each tiny spiral or elliptical shape, represented an entire galaxy containing billions of stars, and many of these objects were being seen clearly for the first time in human history. To understand what makes a deep field image so scientifically valuable, we must consider what happens when we point a telescope at a seemingly empty patch of sky and allow it to gather light for extended periods of time. In visible light, most directions in the sky appear dark to the naked eye, with only the nearest stars and the diffuse band of our own galaxy providing obvious luminosity. But when a sensitive instrument stares at one of these apparently vacant regions for hours or days, the faint light from millions of distant galaxies gradually accumulates on the detector, revealing an astonishing cosmic abundance. Hubble demonstrated this capability with its original deep field image in 1995, and subsequent observations confirmed that nearly everywhere we look, the universe is filled with galaxies extending to the limits of our observational ability. Webb's SMACS 0723 image built upon this tradition, but added capabilities that Hubble simply could not match, penetrating deeper into the infrared and achieving resolution that transformed smudges into detailed structures. Where Hubble saw blurred patches of light, Webb revealed spiral arms, central bulges, and galactic interactions, each feature visible with a precision that allowed astronomers to study individual characteristics of galaxies billions of light-years away. Some of these galaxies appeared stretched into long arcs, their light bent by the gravitational field of the cluster, creating what astronomers call Einstein rings and gravitational lensing effects first predicted over a century ago. The cluster itself, that massive collection of galaxies in the foreground, was acting as a natural telescope, its gravity magnifying and amplifying the light from even more distant objects that would otherwise remain beyond detection. Gravitational lensing is one of the most remarkable predictions of Einstein's general theory of relativity, demonstrating that mass actually curves the fabric of space-time itself, bending the path that light travels. When a massive object like a galaxy cluster sits between us and a more distant source, light from that distant source follows curved paths around the intervening mass, sometimes reaching us from multiple directions simultaneously. This effect can magnify the distant object by factors of 10 or more, effectively boosting our telescope's power and revealing details that would otherwise require instruments far larger than any we could construct with current technology. The SMAC 0723 cluster contains enormous quantities of both visible matter and invisible dark matter, and together this mass creates a gravitational lens of sufficient strength to probe the early universe with remarkable efficiency. In the Webb image, you can trace the gravitational lensing effects by looking for galaxies stretched into arcs and curves, each distortion revealing the presence of mass in the foreground cluster that is bending the light. Some background galaxies appear multiple times in the same image, their light taking different paths around the cluster and arriving at our telescope from different angles as multiple images of the same original object. By analyzing these multiple images and measuring their positions and distortions, astronomers can map the distribution of mass in the cluster, including dark matter that emits no light at all. This technique, called gravitational lensing mass mapping, reveals that most of the cluster's mass is invisible, composed of dark matter whose nature remains one of the deepest mysteries in modern physics. The galaxies visible in this deep field span an enormous range of cosmic history, from relatively nearby objects to some of the most ancient structures ever observed, each one appearing to us as it was when its light departed on its journey toward our detectors. Light from the nearest galaxies in the image may have traveled only a few 100 million years, while light from the most distant objects began its journey when the universe was less than 1 billion years old. This means that a single image contains snapshots of cosmic evolution spanning over 12 billion years, allowing astronomers to study how galaxies have changed and developed across the majority of cosmic history. The Webb Deep Field is not merely a photograph, but a time machine, sampling the universe at different epochs simultaneously and providing a comparative record that reveals the processes by which galaxies grow and evolve. When astronomers examined the SMAC 0723 image in detail, they immediately began identifying objects worthy of follow-up study, measuring redshifts to determine distances, and selecting candidates for spectroscopic observation. The redshift of a galaxy tells us how much the universe has expanded since the galaxy's light was emitted, with higher redshifts indicating more ancient objects whose light has been stretched by greater amounts of cosmic expansion. Some of the objects in this image showed redshifts exceeding 8 or 9, meaning their light departed when the universe was less than 600 million years old, representing some of the most ancient galaxies ever, spectroscopically confirmed at the time of observation. These measurements transformed beautiful points of light into scientific data points, anchoring each galaxy in cosmic history and allowing researchers to begin understanding how star formation and galaxy growth proceeded in the early universe. The spectroscopic capabilities of Webb proved essential for understanding what these ancient galaxies contained, revealing chemical compositions and physical conditions that illuminated the nature of stellar populations billions of years in the past. When light passes through gas in a galaxy, certain wavelengths are absorbed by specific chemical elements, creating absorption lines that act as fingerprints, identifying the presence of hydrogen, helium, oxygen, and other elements. Similarly, hot gas emits light at characteristic wavelengths, producing emission lines that reveal temperatures and densities, allowing astronomers to measure conditions within distant galaxies without ever visiting them. Webb's near-infrared spectrograph could analyze dozens of objects simultaneously, gathering chemical information across the entire field of view, and building a census of elemental abundances across billions of years of cosmic history. What surprised many researchers was how quickly the early universe had produced heavy elements, the atoms created by stellar fusion and supernova explosions, elements that should require multiple generations of stars to accumulate in significant quantities. Even galaxies observed just a few 100 million years after the Big Bang showed evidence of oxygen and carbon, suggesting that star formation in these ancient systems had proceeded with remarkable intensity and efficiency. The first stars formed from primordial hydrogen and helium must have lived fast and died explosively, seeding their surroundings with heavier elements that were then incorporated into subsequent stellar generations. Webb was providing a window into this rapid chemical enrichment, revealing how quickly the universe transitioned from the pristine simplicity of the Big Bang to the complex elemental diversity that would eventually make planets and life possible. The image also captured galaxies in the process of interacting and merging, their structures distorted by gravitational encounters with neighbors. A reminder that cosmic evolution is often violent rather than peaceful in nature. These interactions trigger bursts of star formation as gas clouds collide and compress, lighting up galaxies with brilliant displays of stellar birth that can be detected across billions of light years. Some of the disturbed galaxies in the SMACS field showed exactly these signatures, with unusually high rates of star formation, suggesting that they were captured in the midst of transformative merger events that would eventually reshape them entirely. Over time, merging galaxies settle into new configurations, their stars mixing and their central black holes eventually coalescing, building the larger, more massive galaxies we observe in the nearer, more recent universe. For the general public, perhaps the most striking aspect of the image was its sheer aesthetic beauty, a composition of color and form that seemed almost artistic in its visual impact. But every color in this image carries scientific meaning, representing specific wavelengths of infrared light translated into visible hues for human perception, with redder colors indicating longer wavelengths and bluer colors representing shorter wavelengths within Webb's infrared range. The orange and red galaxies in the image are typically the most distant, their light stretched to longer wavelengths by cosmic expansion, while the bluer objects are generally nearer and less affected by redshift. This color coding allows even casual observers to roughly estimate which objects are ancient and which are relatively recent, making the image not just beautiful, but scientifically informative at a glance. The diffraction spikes visible on bright stars in the image, those distinctive six-pointed patterns, are artifacts of Webb's hexagonal mirror design, and they provide a visual signature that distinguishes Webb images from those of other telescopes. Each spike is created by light diffracting around the struts that support the secondary mirror, and the gaps between mirror segments, producing a pattern that becomes especially prominent around bright point sources like stars in our own galaxy. While stars in our Milky Way are relatively nearby, typically within a few thousand light years, they can appear quite bright and produce these distinctive patterns that help viewers distinguish them from distant galaxies. The galaxies themselves, even the brightest ones, are too far away to produce such spikes. Their light spread across enough angular extent to avoid the diffractive effects that create these striking stellar patterns. As researchers continued examining the SMACS deep field, they realized it was not just a single observation, but a template for future investigations, demonstrating techniques that could be applied to other regions of sky and other gravitational lens systems. The combination of deep imaging and spectroscopy through a foreground lens proved extraordinarily efficient, allowing Webb to reach objects that would otherwise require impossibly long exposure times to detect with any instrument. Other galaxy clusters have since been observed using similar strategies, each one providing another natural telescope that magnifies the distant universe and brings the earliest galaxies within reach of detailed study. This approach was pioneered with Hubble, but has reached full maturity with Webb, transforming galaxy clusters from objects of study into tools that extend our observational capabilities far beyond what the telescope alone could achieve. The emotional response to this first image was significant, with astronomers and members of the public alike expressing awe at what had been revealed. A reaction that reflected not just the image's beauty, but its profound implications for our understanding of cosmic history. Here was proof that the decades of effort and billions of dollars invested in Webb had been justified, that the telescope worked as designed and would deliver transformative science for years to come. Social media filled with comments from people who found themselves moved by the image in ways they had not anticipated, expressing a sense of connection to the distant universe that transcended purely intellectual engagement. Something about seeing so many galaxies in such clarity touched a collective nerve, reminding viewers of both our cosmic insignificance and our remarkable ability to comprehend such vastness. In the days following the image release, research teams around the world began writing proposals for follow-up observations, identifying specific objects in the field that warranted deeper study and detailed spectroscopic analysis. The telescope's time is precious and carefully allocated through competitive review processes, with scientists submitting proposals that are evaluated for scientific merit and technical feasibility by expert panels. An image like SMACS 0723 generates dozens of such proposals, each focused on different aspects of what the observation revealed, from individual galaxy properties to statistical analyses of population characteristics across the full sample. Webb's first deep field was thus not an endpoint, but a beginning, opening avenues of research that would keep astronomers occupied for years as they mined the data for every fragment of scientific insight it contained. The universe revealed in that single image contained more complexity than any human lifetime could fully explore, and yet there it was, compressed into a frame that could be viewed on a phone screen or printed on a poster. This democratization of cosmic imagery represents something profound about our era of astronomical exploration, where the most distant reaches of the universe become accessible to anyone with an internet connection. Children, looking at this image, might someday become the scientists who interpret its mysteries, inspired by a first glimpse of thousands of galaxies captured by a golden telescope stationed 1,000,000 miles from Earth. For now, we can simply appreciate what has been revealed, letting the scale and beauty of the deep field settle quietly into our awareness as we prepare to travel even further back in time to see what Webb has discovered at the very edge of the observable universe. Next, we will explore how light serves as a time machine, carrying information across billions of years and allowing Webb to witness the cosmos in its infancy. Light travels at an extraordinary but finite speed, covering nearly 300,000 kilometers every second. And this means that every observation we make of the universe is necessarily a look into the past of whatever we observe. When you look at the moon, you see it as it was about 1.3 seconds ago, because that is how long the reflected sunlight requires to travel the distance from the lunar surface to your eyes. When you observe the sun, you see it as it was approximately 8 minutes in the past. And when you look at the nearest star beyond our solar system, you see it as it was 4 years ago. This fundamental aspect of light's finite speed transforms every telescope into a time machine, revealing not the universe as it currently exists, but as it existed when the light we detect first began its journey. For objects within our solar system, or even our galaxy, this delay is relatively modest and makes little practical difference, since planets and nearby stars change slowly enough that observations from years or decades past remain relevant to current conditions. But when we observe galaxies billions of light years away, we are seeing them as they were billions of years ago, and the universe has changed dramatically during the interval that light has been traveling toward us. A galaxy observed at a distance of 10 billion light-years appears to us as it was 10 billion years ago, when the universe itself was less than 4 billion years old and cosmic conditions were substantially different from today. Webb's ability to see extremely distant objects means it can effectively peer into the early universe, witnessing galaxies and stars as they existed during the first chapters of cosmic history. This temporal depth becomes scientifically meaningful when combined with our understanding of cosmic expansion, the ongoing stretching of space itself that carries galaxies apart from one another over cosmic timescales. When light leaves a distant galaxy, it begins its journey through a universe that is expanding, and as that light travels, the space through which it moves continues to stretch in all directions simultaneously. This expansion has a remarkable effect on the light itself, stretching the wavelength of each photon proportionally to the expansion, so that light which departed as visible wavelengths arrives at our detectors as longer infrared wavelengths. The amount of this stretching, called redshift, directly measures how much the universe has expanded since the light was emitted, and therefore tells us both the distance to an object and the epoch at which we are observing it. Astronomers quantify this stretching using a value called Z, which describes the fractional increase in wavelength, with higher Z values indicating greater redshifts and therefore more ancient objects whose light has traveled longer. An object at redshift Z equals 1 has had its light wavelength doubled by cosmic expansion, meaning we observe it as it was when the universe was roughly half its current age of approximately 13.8 billion years. At redshift Z equals 10, the light has been stretched by a factor of 11, and we are observing the object as it was when the universe was only about 500 million years old, and cosmic dawn was just beginning. Webb has detected objects at redshifts exceeding 13, representing light that departed when the universe was barely 300 million years old, providing unprecedented views of the primordial universe during the epoch when the first stars and galaxies were forming. Understanding redshift requires appreciating that space itself is what expands, not the galaxies moving through static space. A distinction that was counterintuitive when first proposed, but is now fundamental to cosmological understanding. Imagine dots drawn on the surface of a balloon that is being inflated, with each dot representing a galaxy, and the balloon surface representing the fabric of expanding space-time. As the balloon inflates, every dot moves away from every other dot, not because the dots are moving across the surface, but because the surface itself is stretching and increasing the distance between all points simultaneously. Light traveling between dots during this expansion gets stretched along with the space through which it moves, arriving with longer wavelengths that betray the expansion that occurred during its journey across the cosmos. For Webb, this cosmological redshift is not an obstacle but an opportunity, shifting the ultraviolet and visible light from ancient galaxies into the infrared wavelengths where the telescope's instruments are most sensitive. The first stars and galaxies emitted much of their light at shorter wavelengths, including ultraviolet radiation from hot young stars. But after traveling for billions of years through expanding space, that light has shifted into the infrared spectrum. Hubble, which primarily observed invisible and near-infrared wavelengths, could detect galaxies out to redshifts of about 11. But the most distant objects were at the very edge of its capability and appeared as little more than faint smudges. Webb's infrared sensitivity extends much further, detecting light that has been stretched beyond Hubble's range and capturing the oldest photons with enough clarity to reveal detailed structure and spectroscopic information. The light arriving at Webb's detectors from the most distant sources carries information about conditions that no longer exist anywhere in the universe, representing a cosmic era that ended billions of years before Earth formed or our sun ignited. The early universe was denser, hotter, and filled with radiation that bathed everything in a cosmic glow. Conditions that gradually changed as expansion cooled the cosmos and allowed matter to clump into the first gravitational structures. By observing light from this era, we can test our theories about how the universe evolved. Comparing what we see with predictions from cosmological models that describe expansion, cooling, and structure formation, every discrepancy between observation and prediction is an opportunity to refine our understanding. And Webb has already revealed surprises that are causing theorists to reconsider aspects of their models. There is a limit to how far back we can see using light, imposed by the conditions of the very early universe, when temperatures were so high that atoms could not form and the cosmos was filled with an opaque plasma of charged particles. Before the universe was about 380,000 years old, light could not travel freely through space because photons were constantly scattering off the charged particles that filled the dense early cosmos. Only when the universe cooled enough for atoms to form did space become transparent, releasing a flash of light that we now detect as the cosmic microwave background radiation pervading all of space. This background represents the oldest light in the universe, and we cannot see further back using electromagnetic radiation because before this epoch, the universe was opaque and no light from earlier times survives. Webb cannot see the cosmic microwave background directly, as that radiation has wavelengths far longer than its instruments detect, but it can see light from the era immediately following, when the first stars and galaxies were forming in a transparent cosmos. This era, sometimes called cosmic dawn, represents the transition from a universe filled with dark neutral gas to a universe illuminated by stellar light, and eventually reionized by the intense radiation from early stars. The first galaxies were likely small and irregular, their stars forming from primordial gas with no heavy elements, and Webb has now detected light from some of these primitive systems, providing our first direct glimpse of cosmic dawn. Understanding this transition is crucial for cosmology, as it marks the beginning of the stellar era, the epoch during which stars and galaxies would build the elements and structures that eventually made planets and life possible. When we observe a galaxy at redshift 13, we must remember that the light we detect has been traveling for approximately 13.4 billion years, and the object that emitted this light has been carried further away by cosmic expansion during the time the light was traveling. This is a subtle but important distinction, as the current distance to such an object is much greater than the distance the light traveled, because space has continued to expand while the photons were in transit. Astronomers distinguish between light travel distance, which measures how long light has been journeying, and co-moving distance, which accounts for expansion and describes where the object is now relative to us. These distinctions become important for precise cosmological calculations, though for appreciating the basic time travel nature of astronomy, it suffices to know that ancient light reveals ancient conditions that preceded our own existence by billions of years. The images Webb captures of these ancient galaxies are more than pretty pictures. They are data sets rich with information about stellar populations, gas conditions, and chemical abundances at cosmic dawn. By analyzing the colors of these galaxies, astronomers can estimate the ages and temperatures of their stellar populations, determining whether the stars are young and hot or older and cooler based on the wavelengths of light they emit. Spectroscopy reveals even more, identifying specific elements and their abundances through characteristic absorption and emission lines, building a chemical inventory of the early universe that tells us how quickly stellar nucleosynthesis proceeded. Each galaxy represents a laboratory that existed billions of years ago, its conditions recorded in the light it emitted, and Webb is now reading those ancient records with unprecedented precision and clarity. One remarkable aspect of observing the distant universe is that we cannot observe the current state of these ancient galaxies, because the light from their current condition has not yet had time to reach us and will not arrive for billions of additional years. The galaxies we see at cosmic dawn have evolved continuously since the light we observe was emitted, growing through mergers, forming new generations of stars, and likely becoming very different objects than what we currently see. Some may have merged into larger structures, while others may have exhausted their gas and faded into quiet elliptical systems, their current appearance unknown and unknowable to us at this moment in cosmic history. We can only study the early universe by observing it directly, seeing what it was rather than what it has become, and trusting that the physical laws governing cosmic evolution are consistent enough to connect past observations with present-day understanding. The finite speed of light also means that simultaneity across cosmic distances is fundamentally meaningless, since there is no universal present moment that applies everywhere in the expanding cosmos simultaneously. What we call now in our local region of space has no direct correspondence to a simultaneous moment in a galaxy 10 billion light-years away, because the concept of simultaneity depends on your frame of reference and location within the cosmos. This is a deep consequence of Einstein's relativity, which Webb's observations illustrate in a practical way, revealing a universe where time and space are interwoven into a single fabric of space-time that expands and evolves. For our purposes tonight, the key insight is simpler, that looking out into space is looking back in time, and Webb sees the universe's past with a clarity no previous instrument could achieve. As you consider these ideas, you might find a kind of peaceful vertigo in the realization that every distant object visible in the night sky is a message from the past, a record of conditions that have long since changed. The photons striking Webb's detectors tonight departed their sources before complex life existed on Earth, traveling through expanding space while our planet formed, while life evolved, and while civilizations rose and fell unaware of these ancient messengers approaching. There is something quietly profound about this cosmic postal system, these ancient messages arriving after journeys spanning billions of years, finally caught by a golden mirror stationed 1,000,000 miles from a planet that emerged long after the light began its voyage. In this sense, Webb is not just observing the universe, but receiving communications from its distant past, translating photons that left their sources when the cosmos was young into knowledge that enriches our present understanding. So now, we will examine some of the specific galaxies Webb has discovered at these extreme distances, including objects that have challenged our expectations about how quickly structures could form in the early universe. Among Webb's most significant early accomplishments was the detection of galaxies at redshifts higher than any previously confirmed, objects whose light departed when the universe was only a few 100 million years old and cosmic dawn was just beginning. These discoveries came through dedicated survey programs designed to search systematically for the most distant objects, using deep imaging followed by spectroscopic confirmation to measure precise redshift values and verify the ancient nature of each candidate. The JWST survey, standing for JWST, Advanced Deep Extragalactic Survey, became particularly productive in this regard, identifying numerous galaxies at redshifts exceeding 10 and providing detailed characterization of their properties for the first time. What these observations revealed was both confirming and surprising, showing that galaxy formation began early, but also revealing objects more massive and mature than existing theoretical models had predicted. The process of identifying these ancient galaxies requires careful analysis to distinguish truly distant objects from closer ones that might mimic their appearance. Since various effects can cause relatively nearby galaxies to appear red and potentially be confused with genuinely redshifted sources, astronomers use a technique called the Lyman break method, which looks for a characteristic feature in a galaxy's spectrum, where light at wavelengths shorter than a specific limit is absorbed by intervening hydrogen, and the galaxy appears to drop out of images at those wavelengths. The wavelength of this break shifts predictably with redshift, so finding where a galaxy becomes invisible reveals its approximate distance, providing a preliminary estimate that spectroscopy can later confirm with much greater precision. Webb's imaging capabilities allowed researchers to apply this technique at infrared wavelengths, pushing into redshift ranges inaccessible to Hubble, and revealing a population of ancient galaxies that had remained hidden beyond the reach of previous observatories. Spectroscopic confirmation is essential because photometry alone, the measurement of brightness at different wavelengths, can sometimes mislead, with dusty nearby galaxies occasionally mimicking the colors expected from genuinely distant high redshift objects. When Webb's spectrograph analyzes light from a candidate high redshift galaxy, it spreads that light into a spectrum, revealing emission and absorption lines whose wavelengths provide unambiguous evidence of the galaxy's true redshift. The detection of specific lines, particularly those from hydrogen, oxygen, and nitrogen, at wavelengths shifted into the infrared, confirms that the object is genuinely ancient and its light has been stretched by cosmic expansion over billions of years. Several candidates, initially identified at extremely high redshifts, were later revised downward after spectroscopy revealed them to be dusty objects at more modest distances. But many others were confirmed as genuinely ancient systems representing the earliest observable epoch of galaxy formation. The galaxy known as JWST GS Zone 3. 0 became particularly notable as one of the most distant spectroscopically confirmed objects known, with a redshift of approximately 13.2, indicating that we observe it as it was about 320 million years after the Big Bang. At this epoch, the universe was still emerging from its dark ages, the period before the first stars formed, and whatever galaxy populations existed were among the very first gravitationally bound structures to coalesce from the primordial gas. This object appears compact and relatively modest in mass by later standards, consistent with expectations for early galaxy formation, representing a building block that would eventually merge with others to form larger structures over cosmic time. Its detection demonstrated Webb's ability to probe the earliest observable epoch of cosmic structure formation, pushing our observational reach into territory that had previously been purely theoretical and inaccessible to direct measurement. Beyond simply detecting these ancient galaxies, Webb has characterized their properties with surprising detail, measuring star formation rates, stellar masses, and chemical abundances at epochs just a few 100 million years after the beginning of time. These measurements revealed that some early galaxies were forming stars at prodigious rates, converting their gas into new stars very efficiently, as if they were racing to build stellar populations before the universe was even 1 billion years old. The stellar masses inferred for some of these systems were higher than expected, suggesting that galaxy formation began extremely early and proceeded rapidly enough to produce surprisingly mature systems in a remarkably short cosmic time frame. This observation would prove controversial, as we will explore in the next part, challenging existing models of how quickly cosmic structure formation could proceed in the young universe. The chemical compositions of these early galaxies also provided important information about the first generations of stars, since the heavy elements detected in their spectra must have been created by stellar nucleosynthesis and supernova explosions. In the standard picture, the very first stars formed from primordial hydrogen and helium, the only elements produced in the Big Bang itself. And these so-called population 3 stars lived briefly before exploding and seeding their surroundings with heavier elements. Subsequent generations of stars then formed from this enriched gas, incorporating carbon, oxygen, and other elements, and gradually building the chemical complexity that would eventually characterize later stellar populations, including our own Sun. Webb's detection of oxygen and other elements in galaxies at cosmic dawn confirms that at least one generation of stars had already lived and died, enriching the interstellar medium before the galaxies we now observe had assembled. The sizes and shapes of these early galaxies differ from typical galaxies in the present-day universe, appearing more compact and irregular, as would be expected for objects still in the early stages of hierarchical assembly. Many appear as simple clumps or elongated structures without the organized spiral or elliptical forms that characterize mature galaxies, suggesting that they represent fragments that will later merge to form larger systems with more complex morphologies. The compact sizes are particularly notable, with some early galaxies packing substantial stellar mass into regions only a few thousand light-years across, compared to the hundreds of thousands of light-years that span mature spiral galaxies like our own Milky Way. Understanding how these compact early systems evolved into the diverse zoo of galaxy types we observe today requires tracing the processes of merger, accretion, and internal evolution across billions of years of cosmic history. Webb has also detected signs of active galactic nuclei in some of these early systems, suggesting that supermassive black holes were already forming and beginning their growth process within the first few 100 million years of cosmic history. These black holes reveal themselves through the intense radiation emitted by gas falling into their gravitational wells, producing emission lines and spectral features characteristic of active galactic nuclei, even at extreme redshifts. The presence of black holes so early in cosmic history poses challenges for theoretical models of black hole formation, requiring either very massive initial seeds or extremely rapid growth rates to reach the observed masses. Some researchers have proposed that the first black holes formed directly from collapsing primordial gas clouds, bypassing the stellar phase entirely and creating massive seeds that could grow quickly through subsequent accretion. The environment surrounding these early galaxies differed substantially from conditions in the present-day universe, with higher gas densities, more intense radiation fields, and a cosmic medium that was still largely neutral hydrogen. The first galaxies were responsible for reionizing this neutral gas, emitting enough ultraviolet radiation to strip electrons from hydrogen atoms and transforming the universe from a largely opaque fog to the transparent state it maintains today. Webb's observations of early galaxies help constrain when and how this reionization occurred, measuring the properties of galaxies that contributed to this fundamental cosmic transformation that changed the nature of intergalactic space. By the time the universe was about 1 billion years old, reionization was largely complete, and the transparent universe we observe today had emerged from the neutral conditions that preceded it. The discovery of galaxies at cosmic dawn also helps calibrate our understanding of how structure grows through gravity, testing models of dark matter and cosmological parameters that govern the formation of the first gravitational condensations. In the standard model, small fluctuations in the density of matter after the Big Bang gradually grew through gravitational attraction, with slightly denser regions pulling in surrounding material and eventually collapsing to form the first bound structures. These early structures, called dark matter halos, provided the gravitational scaffolding within which ordinary matter could collect and form stars, building the first galaxies inside invisible cocoons of dark matter that continue to surround them today. Webb's observations of early galaxies test whether this picture correctly predicts the abundance and properties of early systems, or whether modifications to our understanding of dark matter or cosmological physics are required. For astronomers, the ability to observe galaxies at cosmic dawn represents the fulfillment of decades of anticipation and planning, finally bringing within reach an epoch that had been theoretically discussed, but observationally inaccessible for most of astronomical history. Every new detection at extreme redshift extends our empirical record further back in time, reducing the gap between the earliest observed objects and the theoretical models that describe primordial conditions. This gap cannot be closed entirely through light observations, since the universe was opaque before about 380,000 years after the Big Bang, but Webb has pushed our direct observations to within a few 100 million years of the boundary of the observable epoch. Future gravitational wave detectors may eventually probe even earlier conditions through entirely different means. But for electromagnetic astronomy, Webb represents the frontier of our ability to witness cosmic history directly. The detection of multiple galaxies at extreme redshifts also enables statistical studies that go beyond individual object characterization, measuring the abundance of early galaxies and comparing with predictions from cosmological simulations that model structure formation. The number of galaxies detected at each redshift and their distribution of masses and luminosities provides constraints on the physical processes that governed early star formation and galaxy assembly. Some early results suggested that galaxies were more abundant than predicted at the highest redshifts, potentially challenging existing models, though careful analysis of selection effects and systematic uncertainties continues to refine these statistical measurements. The coming years will see larger samples and more precise measurements, gradually building a complete census of the earliest galaxy population and testing our theoretical framework against the empirical record preserved in ancient light. As we consider these ancient objects, it is worth pausing to appreciate what we are actually seeing: light from galaxies that formed in a universe utterly unlike the cosmos we inhabit today, yet governed by the same physical laws. The stars in those early galaxies burned through nuclear fusion, just as stars do today, converting hydrogen to helium and heavier elements through the same processes that power our own sun. Gravity drew matter together, radiation pressure resisted collapse, and gas cooled to form dense clouds where stars were born. Physics operating identically across the entire history of the universe, despite the changed conditions from epoch to epoch. This universality of physical law is what makes cosmology possible, allowing us to interpret ancient light using principles established in local laboratories, and trusting that the same physics that operates here and now applied equally at cosmic dawn. Now let's examine a puzzling aspect of these early galaxy observations: the discovery of galaxies that appear too massive and too mature for their age, challenging our models of cosmic evolution. Within months of beginning science operations, Webb had revealed something unexpected about the early universe, discovering galaxies at cosmic dawn that appeared more massive and more mature than theoretical models had predicted would be possible at such early epochs. These objects, bright and apparently well developed, seemed to defy expectations about how quickly structures could form, presenting what astronomers began calling the too big too soon problem that challenged existing frameworks. The stellar masses inferred from Webb observations suggested that billions of solar masses of stars had already formed in galaxies observed less than 500 million years after the Big Bang, when there had seemingly been insufficient time for such extensive star formation. This discrepancy between observation and theoretical expectation sparked intense debate and analysis as researchers worked to understand whether the observations indicated a fundamental problem with cosmological models or whether alternative explanations could resolve the apparent tension. The theoretical framework that predicts galaxy formation timescales is called the lambda-CDM model, combining cold dark matter with a cosmological constant. And this framework has successfully explained a vast range of observations, from cosmic microwave background patterns to the distribution of galaxies in the present-day universe. According to this model, the first dark matter halos massive enough to host galaxy formation should have appeared several 100 million years after the Big Bang, with baryonic matter then falling into these halos and beginning the process of star formation only after sufficient cooling and compression. The rate at which stars form depends on gas density, cooling efficiency, and various feedback mechanisms that regulate the conversion of gas to stars. And standard models suggested that extremely massive galaxies should require more time to assemble than the early universe had provided. Webb's apparent detection of massive galaxies at extreme redshifts seemed to require either much faster assembly than predicted, or a fundamental revision of how we model early cosmic evolution. Initial estimates of stellar masses in these early galaxies relied on fitting observational data to theoretical models of stellar populations, comparing measured brightnesses and colors with predictions for galaxies containing different amounts of stellar mass. These estimates involve significant uncertainties, as the relationship between observable properties and underlying mass depends on assumptions about the ages of stellar populations, the initial mass function of stars, and the amount of dust that may obscure some fraction of the light. Researchers quickly recognized that the most extreme mass estimates might be revised downward upon closer examination if some of the assumptions used in the initial analysis proved overly simplistic or inappropriate for the unusual conditions of cosmic dawn. Nevertheless, even conservative revisions left a population of surprisingly massive early galaxies that challenged expectations, requiring explanation through either astrophysical mechanisms or modifications to cosmological models. One possible resolution involves reconsidering the efficiency of star formation in the early universe, allowing for the possibility that conditions at cosmic dawn favored more rapid conversion of gas into stars than occurs in present-day galaxies. In the contemporary universe, star formation is regulated by various feedback mechanisms, including supernova explosions and radiation pressure, which heat and expel gas from star-forming regions and limit the rate at which new stars can form from available material. These feedback processes might have operated differently when gas densities were higher and metallicity was lower, potentially allowing for bursts of star formation that converted gas to stars with unusually high efficiency compared to later epochs. If early galaxies could transform a large fraction of their available gas into stars within a few 100 million years, then the surprisingly massive systems Webb observed might be explained without requiring modifications to fundamental cosmology. Black holes grow by consuming surrounding matter, which forms hot accretion disks that radiate intensely across a broad range of wavelengths. And this radiation can outshine the stellar population of an entire galaxy if the black hole is massive and actively feeding. If some of the luminosity attributed to stars in early galaxies actually originates from accreting black holes, then the inferred stellar masses would be correspondingly lower, and the tension with theoretical predictions would be reduced. Webb's spectroscopic capabilities have helped distinguish between stellar and black hole contributions in some cases, identifying characteristic emission lines from active galactic nuclei that reveal the presence of accreting black holes in early galaxies. This analysis has confirmed that at least some early galaxies do host active black holes, complicating the interpretation of their total luminosity, but also raising new questions about how such massive black holes could form so early in cosmic history. The question of black hole formation in the early universe has become one of the most actively debated topics following Webb's discoveries, since the presence of massive black holes just a few 100 million years after the Big Bang presents its own theoretical challenges. In the standard picture, black holes form when massive stars exhaust their nuclear fuel and collapse, leaving behind remnants of perhaps 10 to 100 solar masses that must then grow through subsequent accretion over billions of years. For a black hole to reach millions or billions of solar masses, through this process requires sustained feeding at high rates, and the available time in the early universe seems insufficient to grow from stellar mass seeds to the supermassive objects inferred from Webb observations. Alternative formation pathways have been proposed, including direct collapse of massive gas clouds into black holes without an intervening stellar phase, potentially creating more massive initial seeds that require less growth to reach observed masses. The discovery of these unexpectedly massive early systems has motivated careful reanalysis of both observational and theoretical methods, with astronomers examining potential systematic errors and theorists exploring modifications to standard modeling approaches. Some researchers have questioned whether the spectral energy distribution models used to infer stellar masses are appropriate for cosmic dawn conditions, where stellar populations and dust properties might differ from the templates derived from nearby galaxies in the present-day universe. Others have explored whether exotic stellar populations, such as extremely massive early stars with unusual properties, might produce spectra that mimic the signatures of larger stellar masses when analyzed using standard techniques. The resolution of this puzzle will likely require both improved observational constraints and refined theoretical modeling, gradually narrowing the gap between what we observe and what our frameworks predict. From a broader perspective, the tension between Webb observations and theoretical predictions illustrates how science progresses through confrontation between data and theory, with discrepancies serving as signals that our understanding remains incomplete rather than as failures of the scientific method. When Hubble revealed that the universe was expanding, it contradicted the prevailing assumption of a static cosmos, forcing Einstein and others to revise their theoretical frameworks to accommodate observational reality. The apparent excess of massive early galaxies may similarly require revisions to our models, whether in the astrophysics of star formation and feedback, in the cosmological parameters that govern structure formation, or in the black hole formation mechanisms that seed early galaxy growth. Alternatively, the tension may resolve through improved understanding of systematic uncertainties in the observations, demonstrating that the existing framework remains valid once all effects are properly accounted for. What seems clear is that the early universe was a more dynamic and productive environment than many models had anticipated, with structure formation proceeding rapidly enough to build surprisingly substantial systems within the first few 100 million years. Whether this requires fundamental changes to cosmology or simply refined astrophysical modeling remains to be determined through continued observation and analysis. With Webb continuing to discover and characterize early galaxies that will constrain the possible solutions to this puzzle, the telescope's ongoing surveys will eventually provide samples of hundreds or thousands of early galaxies, enabling statistical analyses that can distinguish between competing explanations with greater precision than current observations allow. For now, the too big, too soon problem remains an active area of research and a reminder that even our best models of cosmic evolution contain assumptions that observational data may eventually challenge. The philosophical implications of these discoveries extend beyond technical debates about cosmological models, touching on fundamental questions about how the universe transitioned from smooth primordial conditions to the rich structure we observe today. The emergence of galaxies, stars, and eventually planets and life required this transition from simplicity to complexity, and Webb is now revealing the earliest observable stages of this transformation with unprecedented clarity. Each surprisingly massive early galaxy represents a data point in the story of how matter organized itself under gravity, building the cosmic scaffolding upon which subsequent generations of stars and planetary systems would eventually form. Understanding this process is not merely academic curiosity, but relates directly to our own origins, since the elements in our bodies were forged in stellar furnaces and dispersed by supernovae that occurred billions of years before the sun formed. As these debates continue in scientific journals and conferences around the world, the galaxies themselves remain unchanged at their cosmic distances, their ancient light still traveling toward future observations that will refine our understanding of their properties and origins. The light Webb has already captured from cosmic dawn departed its sources over 13 billion years ago, and those sources have long since evolved into something very different from what we currently observe in our data. We cannot see what they have become, only what they were during that brief epoch when their light first embarked on its journey, carrying information about conditions at cosmic dawn that we can now decode using the most sophisticated astronomical instruments ever constructed. There is something quietly humbling about this one-way communication across cosmic time, receiving messages we can never answer, from objects that have spent billions of years transforming beyond recognition. Okay, now, we will turn from these most distant galaxies to regions much closer to home, where Webb has revealed the hidden nurseries where new stars are being born within our own galaxy. Within the spiral arms of the Milky Way, and scattered throughout other galaxies in the nearby universe, lie vast clouds of gas and dust, where new stars are constantly forming. And Webb has provided our most detailed views of these stellar nurseries through its unique ability to see infrared light that penetrates obscuring material. These regions, called molecular clouds, contain the raw material from which stars condense through gravitational collapse, but they are largely opaque to visible light because the dust grains within them scatter and absorb shorter wavelengths. Hubble could see the surfaces of these clouds and occasionally glimpse stars emerging from their edges, but the interior processes where protostars are actually forming remained hidden behind curtains of dust that blocked optical observations. Webb's infrared vision changes this fundamentally, allowing astronomers to peer through the dust and witness star formation in progress, revealing details of this critical process that shapes the evolution of galaxies and the formation of planetary systems. The physics of star formation begins with gravity, the attractive force that draws matter together across space. And in molecular clouds, this force gradually overcomes the pressure and turbulence that support the gas against collapse in certain regions. These regions of enhanced density, called cores, represent the seeds from which individual stars or small stellar groups will eventually form, condensing over hundreds of thousands of years as gravity pulls material inward toward the growing central concentration. As the core contracts, it heats up from the conversion of gravitational potential energy into thermal energy, and eventually, the central temperature and density reach the conditions necessary for nuclear fusion to ignite, and a true star is born. Before this ignition occurs, the object is called a protostar, still embedded within its natal envelope of gas and dust. And Webb can now observe these protostars directly through the surrounding material that renders them invisible to optical telescopes. One of the most spectacular examples of Webb's ability to reveal hidden star formation came from observations of the Carina Nebula, a massive star-forming region located approximately 7,600 light-years from Earth in the southern constellation of the same name. The image, nicknamed the cosmic cliffs, showed a boundary between dense molecular cloud material and a region of hot ionized gas, with the cliff-like structure sculpted by intense radiation and stellar winds from massive stars that had already formed in the region. In visible light, the cliff face appears as a dark silhouette against the glowing background, with limited detail visible on the dense side. But Webb's infrared view revealed hundreds of previously hidden objects, including young stellar objects still embedded in the cloud material. Jets of material were visible streaming away from newborn stars, and bubble-like structures marked regions where stellar radiation was clearing surrounding gas, transforming our view of a familiar object into a newly detailed understanding of ongoing star formation. The jets emanating from young stars represent one of the most dramatic aspects of the star formation process, as material falling onto the growing protostar is partially redirected into narrow beams that shoot outward at hundreds of kilometers per second. These jets are launched from the inner regions of the accretion disk surrounding the young star, channeled by magnetic fields into collimated streams that can extend for light years through the surrounding molecular cloud. When these jets collide with ambient gas, they create shock waves that heat the material and cause it to glow, producing features called Herbig-Haro objects that astronomers have studied for decades using visible and near-infrared wavelengths. Webb reveals these jets with unprecedented clarity, tracing them from their launch points near the central star through their propagation into the surrounding medium, and providing detailed information about the physical conditions in both the jet material and the environment it impacts. The accretion disks around young stars are not merely transient features of the star formation process, but represent the reservoirs from which planetary systems will eventually form around the nascent stars. These disks of gas and dust orbit the central protostar, gradually feeding material inward to build up the stellar mass, while in their outer regions, the material may begin to clump together and form the seeds of future planets. Webb has observed numerous protoplanetary disks with detail sufficient to reveal gaps and rings in the disk structure, features that may indicate the presence of already forming planets that are gravitationally clearing their orbital zones. By studying disks around stars of different ages, astronomers can trace the evolution of planetary systems from their earliest stages, building a timeline that extends from initial disk formation through the emergence of fully formed planetary systems like our own. The infrared observations also reveal the chemical complexity of star-forming regions, as gas and ices in molecular clouds contain a rich variety of molecules, including organic compounds that may eventually contribute to the chemistry of forming planetary surfaces. Spectroscopic observations have detected water ice, carbon dioxide, methanol, and more complex molecules within these clouds, providing inventories of the chemical ingredients available as building blocks for planets and potentially prebiotic chemistry. Some of these molecules form on the surfaces of dust grains, where atoms can meet and react in ways not possible in the tenuous gas phase, creating molecular complexity that would later be incorporated into asteroids, comets, and planetary material. Webb's ability to study these ices in detail advances our understanding of how chemical complexity builds throughout the star and planet formation process, eventually producing worlds with the ingredients necessary for life as we understand it. Massive stars, those with masses many times greater than the Sun, play a particularly important role in shaping their surroundings during and after their formation, producing intense radiation and stellar winds that ionize and disperse the natal gas from which they formed. These stars form in the densest regions of molecular clouds, often in clusters where multiple massive stars emerge together, and their collective influence can trigger or suppress further star formation in adjacent regions depending on local conditions. When radiation from a massive star encounters a dense clump of gas, it can compress the clump and trigger gravitational collapse, potentially initiating star formation that would not have occurred without this external trigger from a nearby luminous neighbor. Alternatively, the radiation can heat and disperse the gas before collapse occurs, preventing star formation. And this complex interplay of triggering and suppression determines the overall efficiency of star formation in different environments. The Tarantula Nebula, located in the Large Magellanic Cloud about 160,000 light-years from Earth, provides one of the best laboratories for studying massive star formation, and Webb has captured this region with detail that reveals thousands of previously hidden young stars. This nebula contains some of the most massive and luminous stars known, with masses exceeding 100 times that of the Sun, and their intense radiation has carved elaborate structures in the surrounding molecular gas over millions of years. Webb's observations showed pillars and filaments of dense gas similar to those in our own galaxy, but on a much larger scale, with embedded protostars visible throughout the structures as they continue the process of stellar assembly. The chemistry of the Tarantula Nebula differs from star-forming regions in our galaxy because of its lower abundance of heavy elements, providing a window into star formation under conditions that more closely resemble the earlier universe when fewer stellar generations had enriched the interstellar medium. The process of star formation connects directly to the broader evolution of galaxies over cosmic time, since the rate at which gas converts to stars determines how quickly galaxies build their stellar populations and consume their fuel supply. Galaxies with abundant gas and high star formation rates will quickly produce large numbers of new stars, while those with depleted gas reserves or conditions unfavorable to collapse will form fewer stars and evolve more slowly. By studying star formation in detail within our galaxy and nearby systems, astronomers develop an understanding of the physics involved, which can then be applied to interpret observations of distant galaxies where individual star-forming regions cannot be resolved. Webb's detailed observations of local star formation thus inform our interpretation of integrated galaxy properties at cosmic distances, connecting the physics operating within individual molecular clouds to the evolutionary trajectories of entire galactic systems. The timescales of star formation are long by human standards, but brief in cosmic terms, with the collapse of a molecular cloud core to a main sequence star requiring roughly 1 million years from initial condensation to nuclear ignition. This means that the star-forming regions Webb observes are capturing processes in progress, frozen at various stages of development, with some objects still deeply embedded and others already clearing their surrounding envelopes as they approach the main sequence. By observing many systems at different stages, astronomers can piece together a timeline of the process, much as one might study a forest by observing trees of different ages to understand the progression from seedling to mature tree. Webb's observations contribute to this timeline by revealing the earliest embedded stages that were previously inaccessible, completing our view of the full sequence from initial cloud fragmentation to emergence of young stellar systems. The dust that obscures star-forming regions in visible light is the same material that ultimately aggregates into rocky planets and forms the solid cores of gas giants, connecting the birth of stars to the subsequent formation of planetary systems around them. This dust consists of tiny grains of silicates, carbon compounds, and ice-coated particles produced by previous generations of stars, mixed into the interstellar medium and incorporated into molecular clouds that later collapse to form new stellar systems. Each generation of stars processes this material, creating new elements through nuclear fusion and distributing them through stellar winds and supernova explosions. And the dust in current star-forming regions records this history of stellar nuclear synthesis and interstellar enrichment. Webb's observations of dust properties in star-forming regions advance our understanding of this cosmic recycling, tracing how material flows from dying stars into the interstellar medium and back into new stellar and planetary systems. As we consider these stellar nurseries, there is something peaceful in recognizing that star formation is occurring continuously throughout our galaxy and others, a process that has continued for billions of years and will persist for billions more as galaxies retain their reserves of molecular gas. The Sun formed in such a nursery approximately 4.6 billion years ago, along with sibling stars that have long since dispersed throughout the galaxy, and the material that became Earth condensed from the disk of gas and dust that surrounded the young Sun. We are connected to these distant star-forming clouds not merely as observers, but as products of the same process, our atoms forged in previous stellar generations and incorporated into the cloud from which our own system formed. This continuity across cosmic time, the ongoing cycle of stellar birth and death and rebirth, represents one of the most profound insights of modern astrophysics, and a theme that Webb illuminates with unprecedented clarity. Let us now return to a familiar target that Webb has revealed in stunning new detail: the pillars of creation in the Eagle Nebula. Among the most iconic images in the history of astronomical observation are the pillars of creation, three towers of gas and dust in the Eagle Nebula, photographed by Hubble in 1995. And Webb has now provided a dramatically different view of these familiar structures by revealing what lies hidden within their dusty interiors. The original Hubble image showed the pillars in visible light, their surfaces glowing with the characteristic reddish hue of ionized hydrogen, while their dense cores appeared as dark silhouettes, blocking the light from stars and nebula material behind them. This image captured the public imagination and became one of the most reproduced astronomical photographs in history, gracing posters, book covers, and museum walls as an emblem of cosmic beauty and the power of modern space telescopes. Yet for all its aesthetic impact, the Hubble image could not reveal what was happening inside the pillars, where the dense gas and dust hid ongoing star formation from view at optical wavelengths. Webb observed the pillars of creation in October 2022, turning its infrared instruments toward this familiar target to demonstrate capabilities that Hubble could not match. And the resulting image revealed the pillars in an entirely new light that transformed scientific understanding. The dense cores that appeared as dark silhouettes in the Hubble image became partially transparent at infrared wavelengths, allowing Webb to detect hundreds of stars forming within the pillars that had been completely invisible in previous observations. Young stellar objects in various stages of formation appeared throughout the structures, some still embedded in thick envelopes of dust, while others had begun to emerge and clear their immediate surroundings of natal material. The transformation was striking, showing that these pillars are not merely beautiful formations, but active stellar nurseries, continuously producing new stars that will eventually emerge to populate the surrounding region of the Eagle Nebula. The pillars of creation are located approximately 6,500 light-years from Earth in the constellation Serpens, within a larger star-forming region designated Messier 16 or the Eagle Nebula that spans tens of light-years across. The pillars themselves are columns of relatively dense molecular gas and dust protruding into a cavity that has been cleared by radiation from nearby massive stars, with the longest pillar extending approximately 4 light-years from base to tip in a structure that dwarfs our entire solar system. This sculpting of dense material by stellar radiation is called photoevaporation, as ultraviolet light heats and disperses the surfaces of the cloud, gradually eroding the structures, while simultaneously triggering star formation within the compressed material. The bright edges visible in both Hubble and Webb images trace this interface between cold molecular gas and hot ionized plasma, marking the boundary where radiation from nearby massive stars is actively processing the cloud material. The young stars visible within the pillars in Webb's infrared view appear as bright points with characteristic diffraction spikes, some surrounded by reddish nebulosity, indicating the presence of dust and gas still associated with ongoing accretion processes. Many of these objects are protostars, still actively gathering mass from their surroundings, too young to have begun nuclear fusion, and their luminosity comes from the gravitational energy released as material falls onto their growing central concentrations. Others have progressed further toward the main sequence and may already be fusing hydrogen in their cores, though they remain embedded in enough dust to have been invisible at the optical wavelengths where Hubble observed. The census of young stellar objects within the pillars provides information about the rate of star formation in these structures and helps astronomers understand how efficiently molecular cloud material converts to stars under the influence of nearby massive stellar radiation. Webb observed the pillars of creation using both its near-infrared camera, NIRCam, and its mid-infrared instrument, MIRI. And the two images reveal complementary aspects of the structures that depend on wavelength in illuminating ways. The NIRCam image, taken at shorter infrared wavelengths, shows the stars most prominently, with the gas and dust appearing as translucent, rusty orange material, while the MIRI image at longer wavelengths emphasizes the dust itself and reveals it as cooler material glowing with thermal emission. In the MIRI image, the newly forming stars are less prominent because young protostars emit most strongly at shorter wavelengths, while the dust dominates the scene with its own thermal glow produced at temperatures of a few hundred degrees Kelvin. Comparing these two views illustrates how observing at different wavelengths reveals different aspects of the same structures, with each wavelength range contributing unique information that together provides a more complete understanding. The edges of the pillars in Webb's images show wavy lines and undulating patterns that trace the interaction between the dense cloud material and the intense radiation from nearby massive stars, a process that occurs over timescales of hundreds of thousands of years, but is frozen in these observations. Some regions show finger-like protrusions extending from the main pillars, and at the tips of several of these fingers, small bright objects are visible that represent stars in the final stages of emerging from their natal cocoons of gas and dust. These protostars are on the verge of separating from the pillar material entirely, having consumed or dispersed most of their immediate surroundings, and they will soon join the population of young stars that illuminate the broader region of the Eagle Nebula. The process repeats continuously as radiation eats away at the pillars and triggers new episodes of star formation within them. though eventually the pillars themselves will be entirely dispersed and only their stellar offspring will remain. The fate of the pillars of creation has been a subject of some debate among astronomers, with some evidence suggesting that a supernova explosion may have already destroyed them from our perspective of cosmic time. Infrared observations of hot dust near the pillars have been interpreted as possible evidence of a supernova blast wave approaching the structures. And if this interpretation is correct, the pillars we observe may have already been destroyed by the shock wave some 6,000 years ago. We would not see this destruction for another approximately 1,000 years, since light from the event has not yet reached Earth, meaning our current observations show the pillars as they existed before their potential destruction by the approaching blast wave. Whether or not this specific scenario is correct, the pillars will eventually be eroded and dispersed by the continued action of stellar radiation as the Eagle Nebula evolves and the massive stars within it run through their life cycles. The comparison between Hubble and Webb images of the pillars of creation provides a powerful demonstration of how wavelength affects our view of the cosmos, and how different instruments reveal different aspects of the same astronomical objects. The two images show the same structures, captured from the same general vantage point in the solar system, yet they appear remarkably different because of the distinct wavelength ranges to which each telescope is sensitive. Hubble's visible light image emphasizes the hot ionized gas and the boundary where stellar radiation meets the cold cloud, while Webb's infrared image penetrates the dust to reveal the embedded stellar population forming within the pillars. Together, these views provide a more complete understanding than either could offer alone, illustrating the value of multi-wavelength astronomy that combines observations across the electromagnetic spectrum. For the millions of people who encountered the pillars of creation through Hubble's famous image, Webb's new view offers both confirmation and revelation, showing that these beloved structures are even more dynamic and productive than their iconic appearance had suggested. The aesthetic power of the original image derived partly from its mystery, the dark silhouettes hinting at unknown depths within the pillars, and Webb has now illuminated those depths to show active star formation proceeding continuously within these cosmic columns. The new image is no less beautiful, with its rusty, translucent appearance and scattered points of stellar light, and it adds scientific substance to aesthetic appreciation by revealing the physical processes responsible for the pillar's appearance. This combination of beauty and understanding represents one of the great gifts of modern astronomy, allowing us to appreciate cosmic objects both emotionally and intellectually through images that inform as they inspire. The pillars also serve as a reminder that star formation is an ongoing process in our galaxy, not merely a historical event that produced existing stellar populations, but a continuous activity that has proceeded for billions of years and will continue for billions more. New stars are forming tonight within molecular clouds throughout the Milky Way, adding to the galactic population through processes similar to those visible in the pillars of creation, converting interstellar gas into new stellar generations that will live their lives and eventually return material to the interstellar medium. This cycle of stellar birth and death drives the chemical evolution of galaxies, building up heavy elements over cosmic time, and ensures that molecular clouds available for future star formation are progressively enriched with the products of stellar nucleosynthesis. We are participants in this cosmic cycling, our atoms having passed through previous stellar generations, and the pillars of creation show this process continuing in one small region of our vast galaxy. As the hours grow later, and the concepts settle quietly into thought, the pillars stand in our imagination as monuments to cosmic creativity. Structures that will eventually dissolve, but whose stellar offspring will persist for billions of years. The stars forming within them will eventually emerge to live their own lives, some brief and violent, others long and steady like our sun, providing stable energy for whatever planetary systems may form around them. A few of these stars may one day host worlds where observers could look back toward our solar system, seeing our sun as a faint point of light and wondering whether anyone there had ever looked in their direction. Such reflections carry us beyond the strictly scientific into the contemplative, where the facts of astronomy blend with the wonder of knowing our place within this vast ongoing process. Next, we will turn from stellar birth to stellar death, exploring Webb's observations of the beautiful and complex structures created when stars reach the end of their lives. Every star that forms from the gravitational collapse of molecular cloud material will eventually exhaust its nuclear fuel and die. And the manner of this death depends primarily on the mass of the star and determines what remnant and surrounding structures it leaves behind. Stars like our sun will end their lives relatively quietly, shedding their outer layers as expanding shells of gas called planetary nebulae, while their cores contract to form dense white dwarf remnants that slowly cool over billions of years. More massive stars meet more violent ends, exploding as supernovae that briefly outshine entire galaxies, and leaving behind neutron stars or black holes depending on how much mass remains in the collapsed core. Webb has observed examples of both types of stellar death, revealing the intricate structures created as dying stars return material to the interstellar medium, material that will eventually be incorporated into new generations of stars and planetary systems. The Southern Ring Nebula, also known as NGC 3132, was among the first targets released during Webb's initial image unveiling in July 2022, and its observation demonstrated the telescope's ability to reveal fine details in the shells of gas expelled by dying stars. This planetary nebula, located approximately 2,500 light-years from Earth, is powered by a binary star system at its center, with the fainter of the two stars being the actual white dwarf remnant that shed the nebula material, while its brighter companion is an unrelated star along our line of sight. Webb's infrared images revealed at least two distinct shells of material surrounding the central star, along with complex structures and irregularities that trace the history of mass loss episodes over the past few thousand years as the star evolved through its final stages. The detail visible in Webb's view far exceeded what previous observations had shown, revealing intricate patterns that record the dynamics of stellar death with unprecedented precision. Planetary nebulae, despite their name, have nothing to do with planets and were misnamed by early observers who thought their round, fuzzy appearance resembled planetary disks and instead represent the final evolutionary stages of stars with masses roughly between 1 and 8 solar masses. As these stars exhaust the hydrogen in their cores, they expand into red giant phases and begin to lose mass through stellar winds, shedding significant fractions of their original material into surrounding space over periods of thousands to millions of years. Near the end of this process, more intense episodes of mass loss can eject substantial shells of material relatively quickly, and these shells are then ionized and illuminated by ultraviolet radiation from the hot central remnant as it contracts toward white dwarf temperatures. The resulting nebulae display remarkable variety in their structures, from simple spherical shells to intricate butterfly shapes and complex asymmetric forms, reflecting the diversity of conditions during the mass loss episodes that created them. The variety of planetary nebula shapes has puzzled astronomers for decades, since simple models of stellar mass loss would predict roughly spherical expansion, and the observed complexity suggests additional factors such as binary companions, magnetic fields, or rapid rotation influence the ejection geometry. Webb's observations of the Southern Ring Nebula provided evidence that its complex structure results at least partly from binary interactions, with material ejected in episodes modulated by the orbital dynamics of the central stellar pair. The companion star's gravity can shape the outflowing material, creating spiral patterns and asymmetries not possible in isolated stellar evolution, and Webb's detail revealed structures consistent with such interactive mass loss scenarios. Understanding how binary companions influence planetary nebula morphology advances our knowledge of the final stages of stellar evolution and helps explain the remarkable diversity of shapes observed among these beautiful astronomical objects. Beyond planetary nebulae, Webb has also observed the remnants of more violent stellar deaths, including supernova remnants where the explosive demise of massive stars has scattered heavy elements throughout surrounding interstellar space. Cassiopeia A, the remnant of a supernova that exploded approximately 340 years ago, as observed from Earth, was imaged by Webb with unprecedented infrared detail, revealing the distribution of silicon, sulfur, argon, and other elements synthesized in the explosion and its immediate aftermath. The supernova that created this remnant was among the most recent in our galaxy, and its proximity allows detailed study of the explosion products, providing information about the nucleosynthesis processes that occur in the cores of massive stars and during the supernova explosion itself. The elements scattered by this single event include significant quantities of material essential for planet formation and life, demonstrating how supernovae enrich the interstellar medium with the chemical ingredients necessary for cosmic evolution. The physics of core collapse supernovae represents one of the most extreme environments in the universe, with the core of a massive star collapsing in less than a second to form a neutron star or black hole, while the outer layers are ejected at significant fractions of the speed of light. During this brief moment, temperatures and densities reach values sufficient to synthesize heavy elements through rapid neutron capture, a process called the R process that is responsible for producing elements like gold, platinum, and uranium that cannot form through normal stellar fusion. The distribution of these elements in supernova remnants, like Cassiopeia A, provides constraints on theoretical models of this nucleosynthesis, testing our understanding of the extreme physics that operates during these catastrophic stellar explosions. Webb's observations contribute to this effort by mapping element distributions with detail not previously possible, tracing how explosion products expand and mix as the remnant evolves over centuries and millennia. The material expelled by dying stars, whether through the gentle mass loss of planetary nebulae or the violent explosions of supernovae, represents the mechanism by which heavy elements are distributed throughout galaxies and made available for incorporation into new stellar and planetary systems. The Sun formed from a molecular cloud that had been enriched by many previous generations of stellar death, and the heavy elements in our solar system, from the iron in our blood to the silicon in our rocks, were synthesized in stellar interiors and dispersed through these death processes. This cosmic recycling connects us directly to the dying stars that Webb observes, Since the atoms in our bodies passed through similar processes billions of years ago before being incorporated into the cloud that became our solar system. Understanding stellar death is therefore understanding part of our own cosmic ancestry, tracing the pathway by which stellar nucleosynthesis products became the building blocks of worlds and life. The timescales of this recycling process span millions to billions of years as material expelled by dying stars disperses through the interstellar medium, eventually mixing with existing gas and dust to form molecular clouds that will someday collapse to create new stellar generations. This continuous cycling means that the interstellar medium becomes progressively enriched with heavy elements over cosmic time, with each stellar generation processing material and adding its nucleosynthetic products to the cumulative reservoir. Webb's observations of both dying stars and forming stars contribute to understanding this cycle, revealing the conditions on both ends of the process that transforms stellar deaths into the raw material for stellar births. Galaxies that have undergone more stellar generations generally show higher metallicities, more heavy elements relative to hydrogen, reflecting the progressive enrichment that results from this ongoing cycling of material through stars. The beauty of planetary nebulae and supernova remnants has captivated observers for centuries, and Webb's images add new dimensions to this aesthetic appreciation, revealing colors and structures invisible to previous instruments while maintaining the visual impact that makes these objects so compelling. The colors in these images encode scientific information, with different hues representing different wavelengths and therefore different physical conditions or chemical species, so that beauty and data are unified in a single visual representation. For the casual viewer, the images offer wonder at the intricate patterns created by physical processes operating across light years, while for the scientist, the same images provide measurements that constrain theories of stellar evolution and nucleosynthesis. This dual nature of astronomical imagery, both beautiful and informative, represents one of the unique aspects of astronomy as a science, where data collection produces objects worthy of gallery display alongside their role in advancing human knowledge. As you consider these dying stars and the material they return to the cosmos, there is a quiet reassurance in the continuity of this cycling, the knowledge that stellar death is not an ending, but a transformation that enables new beginnings. The atoms within you have participated in this cycle at least once, and possibly multiple times, passing through stellar cores where nuclear fusion rearranged protons and neutrons, then being dispersed through stellar winds or explosions. Someday, billions of years in the future, the Sun will undergo its own planetary nebula phase, returning much of its material to the interstellar medium where it may eventually contribute to new stellar and planetary systems. This continuity across cosmic time provides perspective on our place within the larger cosmic story, connecting our brief existence to processes that span the entire history of the universe. In the next part, we will move from stars to the worlds that orbit them, exploring Webb's revolutionary observations of exoplanet atmospheres that are beginning to reveal the conditions on distant worlds. One of Webb's most eagerly anticipated capabilities was its ability to analyze the atmospheres of planets orbiting distant stars, using spectroscopy to identify chemical species and characterize conditions on worlds beyond our solar system. The detection of exoplanets, planets around other stars, has accelerated dramatically since the first confirmed discovery in 1995, and we now know of thousands of these worlds ranging from rocky planets smaller than Earth to gas giants larger than Jupiter. But detecting an exoplanet is only the first step toward understanding it, and characterizing atmospheric composition requires follow-up observations that Webb is uniquely equipped to provide through its infrared spectroscopic instruments. By analyzing starlight that has passed through an exoplanet's atmosphere during a transit, astronomers can identify the spectral fingerprints of molecules that reveal the chemical nature of these distant worlds. The technique used for most atmospheric characterization is called transit spectroscopy, exploiting the geometry that occurs when a planet passes in front of its host star as viewed from Earth, and a small fraction of the starlight filters through the thin atmospheric layer surrounding the planet. During such a transit, the planet blocks some starlight directly, while its atmosphere absorbs additional light at specific wavelengths corresponding to molecules present, creating a distinctive spectral signature that changes the apparent brightness of the star at those wavelengths. By comparing the stellar spectrum during transit to the spectrum outside transit, astronomers can detect the atmospheric absorption features, identifying molecules like water, carbon dioxide, methane, and others by their characteristic fingerprints in the infrared spectrum. Webb's sensitivity and spectral resolution enabled detection of these subtle features at levels impossible for previous instruments, opening atmospheric characterization to a much broader range of exoplanets. Among Webb's early atmospheric observations, the hot Jupiter WASP 39b provided particularly compelling results that demonstrated the telescope's capabilities, revealing a complex atmospheric chemistry that included the first clear detection of carbon dioxide in an exoplanet atmosphere. 39b orbits very close to its host star, completing an orbit in just over 4 Earth days, and the intense stellar radiation heats its atmosphere to temperatures exceeding 900 degrees Celsius, where unusual chemistry can occur. Webb's observations detected water vapor, carbon dioxide, sodium, potassium, and evidence of photochemically produced sulfur dioxide, painting a detailed picture of atmospheric composition that no previous telescope could have provided. The sulfur dioxide detection was particularly significant as it indicated active photochemistry, where stellar radiation drives chemical reactions in the upper atmospheres, demonstrating that exoplanet atmospheres are not static but dynamically evolving under the influence of their host stars. The presence of carbon dioxide in an exoplanet atmosphere has implications beyond simple compositional characterization, since this molecule is relevant to understanding climate processes and the potential habitability of rocky planets around other stars. While WASP 39b is far too hot for life as we know it, the detection of carbon dioxide demonstrates Webb's ability to identify this important greenhouse gas, laying groundwork for future observations of smaller, cooler planets where carbon dioxide abundance relates to climate stability. The carbon cycle on Earth, involving exchange between atmosphere, ocean, and rock, helps stabilize surface temperatures over geological time, and understanding CO2 on other worlds will contribute to assessing whether similar stabilizing mechanisms might operate. Webb's detection at WASP 39b proved that such measurements are possible with current technology, encouraging proposals for observations of more temperate worlds where the implications for habitability are more direct. Webb has also observed smaller planets in the hope of characterizing their atmospheres and determining whether they possess substantial gaseous envelopes, with particular attention to planets in the TRAPPIST 1 system, a collection of 7 rocky worlds orbiting a small, cool red dwarf star about 40 light-years from Earth. This system has attracted intense interest because several of its planets orbit within the habitable zone, the range of distances where liquid water could potentially exist on a planet's surface if atmospheric conditions are suitable. Early Webb observations of the innermost T-A-R-A-P-P-I-S-T1 planets have begun to constrain their atmospheric properties, with preliminary results suggesting that these planets may have thin atmospheres or no atmospheres at all, rather than thick, hydrogen-rich envelopes. These observations are challenging because the planets are small and their host star is relatively faint, requiring careful analysis to extract reliable conclusions about atmospheric presence and composition. The TRAP-PIST-1 results illustrate both the power and the limitations of current atmospheric characterization capabilities, as even Webb struggles to detect the thin atmospheres expected around small, rocky planets. Gas giants and their puffy atmospheres present much larger absorption signals that are relatively easy to detect, while Earth-sized planets with nitrogen-oxygen atmospheres, like our own, produce signals at the edge of detectability, even for Webb's sensitive instruments. Future observations with longer exposure times and improved analysis techniques may yet reveal atmospheres around these worlds. But current results remind us that characterizing Earth-like atmospheres remains at the frontier of technical capability. The search for biosignatures, atmospheric chemicals that might indicate the presence of life, will require either more sensitive instruments or the discovery of more favorable targets where geometry and stellar properties enhance the detectability of atmospheric features. The diversity of exoplanet atmospheres revealed by Webb reflects the remarkable variety of worlds that exist throughout the galaxy, ranging from hot Jupiters with exotic chemistry to warm Neptunes and potentially rocky worlds with compositions unlike anything in our solar system. Some atmospheres appear dominated by water vapor, while others show significant carbon monoxide or methane, depending on temperature and composition. And the patterns emerging from Webb observations are beginning to reveal how atmospheric chemistry varies systematically with planetary properties. These trends provide constraints on planetary formation and evolution theories, testing predictions about how planets acquire their atmospheres and how those atmospheres change over billions of years under stellar irradiation. The connection between atmospheric composition and planetary history makes each spectroscopic observation a window into the formation processes that built these distant worlds, revealing not just current conditions, but clues to the developmental pathways that produced them. Webb's observations extend beyond atmospheric spectroscopy to include thermal emission measurements that reveal temperature profiles and heat redistribution patterns, providing information about atmospheric dynamics and circulation on distant worlds. When a planet passes behind its star from our perspective, its thermal emission temporarily disappears and then returns as it emerges from eclipse, allowing astronomers to measure the planet's own infrared brightness by comparing in-eclipse and out-of-eclipse observations. These measurements reveal the dayside temperature of the planet and, for worlds with significant atmospheres, provide information about how efficiently winds transport heat from the hot day side to the cooler night side. Some hot Jupiters show large day-night temperature contrasts, indicating inefficient heat transport, while others appear more uniform, suggesting differences in atmospheric circulation patterns that relate to composition and other physical properties. The atmospheric observations Webb conducts today establish baseline capabilities and techniques that will be refined and extended in coming decades, building toward the eventual goal of characterizing potentially habitable worlds and searching for signs of life beyond Earth. While this goal remains technically challenging, each observation advances our understanding of exoplanet atmospheres, developing methods and models that will eventually be applied to more Earth-like targets as instrumentation improves. The diversity of atmospheres already detected reminds us that planets are complex systems with varied histories, and assumptions based solely on our solar system may not apply broadly to the full population of worlds throughout the galaxy. Webb is providing the empirical foundation for a new understanding of planetary diversity, one that will eventually inform searches for life and assessments of habitability across a wide range of planetary environments. As you contemplate these distant worlds and their varied atmospheres, consider that each exoplanet observation represents light that has traveled tens or hundreds of light years, carrying molecular fingerprints that reveal the chemistry of worlds we may never visit physically. The same spectroscopic techniques that identify gases in these distant atmospheres are used to study Earth's own atmosphere from space, connecting our understanding of climate and atmospheric chemistry here to the broader context of planetary atmospheres throughout the cosmos. We are learning that planets are common, that atmospheres are varied, and that chemical complexity exists beyond our solar system, expanding our perspective on what kinds of worlds exist and how they form and evolve. This context enriches our understanding of Earth's own uniqueness and commonality, placing our homeworld within a galactic population of planets whose properties we are only beginning to explore. Let us now turn our attention closer to home, examining Webb's observations of planets and other objects within our own solar system. While Webb was designed primarily to observe distant galaxies and characterize exoplanet atmospheres, its instruments have also provided valuable observations of objects much closer to home, revealing new details about the planets, moons, and small bodies of our own solar system. These observations leverage Webb's infrared sensitivity to study thermal emission and molecular absorption features, characterizing surface and atmospheric compositions with capabilities that complement those of dedicated planetary missions. Mars, Jupiter, Saturn, Uranus, Neptune, and their various moons have all been observed by Webb, along with asteroids, comets, and distant icy bodies in the Kuiper Belt beyond Neptune's orbit. Though our solar system has been extensively studied by spacecraft and ground-based telescopes, Webb's unique capabilities have nonetheless produced discoveries and insights, demonstrating that even nearby objects can reveal new secrets when observed with sufficiently advanced instrumentation. Jupiter, the largest planet in our solar system, was among Webb's first solar system targets, and images revealed the giant planet's familiar banded appearance, along with previously unseen details of its polar regions and faint ring system. The Great Red Spot, that iconic storm that has persisted for centuries, appeared bright in Webb's infrared view, indicating high-altitude clouds that reflect sunlight from above the surrounding atmospheric haze layers. Webb also captured Jupiter's aurorae, the glowing polar regions where charged particles from the solar wind and Jovian moons interact with the planet's magnetic field, producing emission features that appear prominently at infrared wavelengths where the telescope observes. The faint rings of Jupiter, much less substantial than Saturn's famous ring system, were visible in Webb's sensitive images, along with several of Jupiter's largest moons that accompanied the planet in the same field of view. Saturn, with its spectacular ring system, has also been observed by Webb with results that revealed the rings in infrared wavelengths, showing thermal emission and reflected sunlight that encode information about ring particle properties and composition. The rings appeared surprisingly dark at some wavelengths where methane in Saturn's atmosphere absorbs strongly, creating contrast between the methane-bright planet and the ice particle rings that lack this absorption feature. Webb's observations complement decades of data from the Cassini spacecraft, which orbited Saturn from 2004 to 2017, providing a different perspective on ring composition and temperature that adds to our comprehensive understanding of this iconic ring system. Saturn's largest moon, Titan, with its thick nitrogen-methane atmosphere, is also of interest to Webb, and observations have detected atmospheric features and surface markings through the hazy atmosphere that usually obscures visibility. The ice giants Uranus and Neptune, the least explored major planets in our solar system, received particular attention from Webb observers, as these distant worlds have been visited by spacecraft only once, during Voyager 2's brief flybys in the 1980s. Webb's observations of Uranus revealed its faint ring system with clarity not achieved since Voyager, showing the narrow rings of dark material that encircle the planet, along with several of its larger moons visible as points of light nearby. The planet's unusual axial tilt, which causes it to rotate nearly on its side relative to its orbit, results in extreme seasonal variations that Webb can track through changes in atmospheric brightness and structure. Neptune observations similarly revealed the planet's ring arcs and atmospheric features, including the faint rings that had not been clearly imaged in decades, and bright clouds that trace dynamic processes in the distant planet's atmosphere. Webb's observations of solar system objects extend beyond the major planets to include their diverse moons, several of which are of particular interest because they may harbor liquid water oceans beneath their icy surfaces and potentially offer environments for life. Saturn's moon Enceladus, known to eject plumes of water vapor from its south polar region, was observed by Webb, revealing the distribution of water vapor in the plume and its spread into a torus of material orbiting Saturn. These plumes, first discovered by the Cassini spacecraft, indicate an active subsurface ocean in contact with rocky material, creating conditions that some astrobiologists consider among the most promising for potential extraterrestrial life in our solar system. Webb's ability to monitor the plume activity and composition from Earth orbit complements what spacecraft have learned during close flybys, and provides ongoing characterization that would otherwise require dedicated missions to maintain. Jupiter's moon, Europa, another ocean world candidate that will be visited by upcoming spacecraft missions, has also been studied by Webb, with observations confirming the presence of carbon dioxide on its icy surface in regions associated with geological activity. The source of this carbon dioxide is of significant interest because it may indicate exchange between the surface ice and the subsurface ocean, potentially providing a pathway for oceanic material to reach the surface where future landers could sample it. Understanding the chemistry of Europa's surface ice informs the design of future missions, which will attempt to characterize the ocean's habitability potential by analyzing surface materials derived from below the ice shell. Webb's detection of carbon dioxide adds to evidence that Europa's surface and ocean are chemically connected, enhancing the scientific value of this moon as a target for astrobiological investigation. Smaller bodies in the solar system have also been observed by Webb, including asteroids and comets, whose compositions provide information about conditions in the early solar nebula, the disk of gas and dust from which our planetary system formed approximately 4.6 billion years ago. These primitive bodies have remained largely unchanged since that early epoch, preserving samples of the original solar system material, and their compositions tell us about the chemistry and temperature conditions at different distances from the young sun. Webb's spectroscopic observations can identify water ice, organic compounds, silicates, and other materials on asteroid surfaces, building a compositional census that relates to our understanding of solar system formation and the delivery of volatiles to the early Earth. Comets, which originate in the outer solar system and carry particularly primitive ice-rich material, are also targets for Webb observations that characterize their compositions as they release gas and dust during close approaches to the Sun. The observations of our solar system's objects demonstrate Webb's versatility as an observatory capable of studying targets at vastly different distances, from galaxies billions of light years away to worlds only hundreds of millions of kilometers from Earth. This range is possible because Webb's infrared sensitivity and spectroscopic capabilities are valuable across this entire span of distances, with similar techniques applied to characterize atmospheres and surfaces, whether the target is a nearby planet or a distant exoworld. The scientific questions are also connected, as understanding our own solar system provides context for interpreting observations of exoplanetary systems, and the diversity of exoplanets revealed by transit surveys informs our appreciation of how unusual or typical our own planetary system may be. Webb serves as a bridge between solar system science and exoplanet studies, applying common methods to both and building a unified understanding of planetary systems in general. For those who grew up with images of the planets from Voyager, Cassini, and other spacecraft, Webb's observations provide a new perspective on familiar worlds, revealing features at wavelengths not accessible from the ground and with sensitivity impossible for earlier space telescopes. The rings of Uranus, the plumes of Enceladus, the clouds of Jupiter all appear in new light that advances scientific understanding, while also providing fresh visual perspectives on worlds that have become familiar through decades of space exploration. There is something reassuring about Webb turning its gaze toward our cosmic neighborhood, as well as the distant universe, connecting our detailed knowledge of the local environment with the broader cosmic context that gives it meaning. These nearby observations remind us that Webb is not merely a telescope for looking far away, but a versatile observatory that enriches our understanding across the full range of astronomical distances. As you consider our solar system's diverse worlds, each with its unique conditions and histories, there is comfort in the detailed knowledge we have gained, understanding that emerges from decades of robotic exploration and continues to grow through observations like Webb's contributions to planetary science. The ice giants remain somewhat mysterious, awaiting future dedicated missions that may not arrive for decades. But Webb provides a bridge of continuing observation that maintains our connection to these distant worlds. Closer to home, the ocean moons of Jupiter and Saturn offer tantalizing possibilities for life beyond Earth, and Webb's characterization of their surface compositions informs the missions that will eventually test these possibilities directly. Our solar system is a laboratory for planetary science, a collection of diverse outcomes from similar starting conditions, and Webb's observations add to our comprehensive understanding of how planets form and evolve. As we come closer to the end, we will zoom out to the largest scales, exploring Webb's observations of galaxy clusters and the large-scale structure of the cosmos. When we step back from individual galaxies and consider the universe at its largest scales, we find that matter is not distributed uniformly through space, but is organized into a vast network of filaments, walls, and clusters that astronomers call the cosmic web of large-scale structure. This pattern emerged from tiny fluctuations in the density of matter in the early universe, which grew through gravitational attraction over billions of years to form the interconnected structures we observe today. Galaxy clusters, the largest gravitationally bound objects in the universe, sit at the intersections of these filaments, containing hundreds or thousands of galaxies embedded within enormous halos of dark matter and surrounded by hot diffuse gas. Webb has observed numerous galaxy clusters with unprecedented detail, revealing both the cluster galaxies themselves and the gravitationally lensed images of background objects that the cluster's immense mass bends and magnifies. The distribution of galaxies and clusters across cosmic space is not random, but follows a pattern set by the primordial density fluctuations, variations imprinted in the first moments after the Big Bang that seeded all subsequent structure formation. These initial fluctuations were extraordinarily small, with density variations of only 1 part in 100,000. Yet, over billions of years, gravity amplified these seeds into the galaxies, clusters, and superclusters that dominate the modern universe. The cosmic microwave background radiation, the afterglow of the early universe's hot, dense phase, preserves a snapshot of these primordial fluctuations, and the pattern of temperature variations in the CMB directly relates to the distribution of structure we observe today. Webb cannot observe the CMB directly, as its wavelengths are too long for the telescope's instruments, but it observes the structures that grew from those early seeds, providing a complementary view of cosmic evolution. Galaxy clusters serve as important cosmological laboratories because their properties depend on the overall parameters of the universe, including the density of dark matter, the nature of dark energy, and the history of cosmic expansion since the Big Bang. By counting clusters at different distances, and therefore different cosmic epochs, astronomers can trace how structure formation has proceeded over time, testing whether observations match predictions from the standard cosmological model or reveal discrepancies requiring new physics. Webb's ability to detect and characterize clusters at high redshifts extends this test to earlier cosmic times than previously accessible, where theoretical predictions are more uncertain and observational constraints are most valuable for discriminating between competing models. The cluster observations also reveal individual galaxies within these dense environments, allowing study of how environment affects galaxy evolution, comparing cluster members to galaxies in less dense regions to understand environmental influences on star formation and morphology. The dark matter that dominates cluster mass cannot be observed directly because it does not emit, absorb, or scatter electromagnetic radiation. Yet its presence is revealed through gravitational effects on visible matter and on light passing through the cluster. Gravitational lensing provides the most direct mapping of dark matter distribution, as the bending of background galaxy images traces the total mass regardless of whether that mass is visible, and comparison with the visible galaxy and gas distribution reveals where dark matter concentrates. Webb's deep observations of cluster fields provide thousands of lensed background sources, enabling detailed reconstruction of the dark matter distribution, with resolution sufficient to distinguish between different theoretical predictions for dark matter properties. Some theories predict that dark matter halos should be smooth, while others suggest small-scale substructure, and Webb's lensing observations provide empirical constraints that test these predictions and advance our understanding of dark matter's fundamental nature. The hot gas that pervades galaxy clusters, called the intracluster medium, represents the majority of ordinary matter in these systems, and observations of this gas at X-ray wavelengths complement Webb's infrared view of the cluster galaxies. While Webb cannot observe X-rays, its observations of cluster galaxies and lensed background sources provide complementary information, and multi-wavelength studies combining Webb data with X-ray and radio observations build a complete picture of cluster properties. The interaction between galaxies and the intracluster medium influences galaxy evolution, as gas can be stripped from galaxies as they move through the hot surrounding plasma, suppressing star formation and transforming spiral galaxies into the elliptical and lenticular types that dominate cluster populations. Webb's observations of cluster galaxies reveal these transformation processes through detailed analysis of stellar populations and star formation activity, connecting the large-scale environment to the evolutionary pathways of individual galaxies. Beyond galaxy clusters, the cosmic web includes filaments of matter that connect clusters and contain significant galaxy populations, stretching across tens of millions of light-years in strands that outline the skeleton of large-scale structure. These filaments are more difficult to observe than clusters because their matter is more diffuse. But Webb's sensitivity enables detection of galaxies within filaments and characterization of their properties relative to cluster and field populations. The voids between filaments, vast underdense regions containing few galaxies, occupy most of the volume of the universe, representing the spaces between the structural elements that grew from primordial underdensities in the early cosmos. The contrast between dense clusters, moderate density filaments, and nearly empty voids represents the full range of cosmic environments. And understanding how galaxy properties vary across these environments reveals how large-scale structure influences the smaller-scale evolution of individual systems. The large-scale structure of the universe serves as a fossil record of cosmic history, preserving information about conditions at various epochs, and comparison with theoretical simulations allows astronomers to test our understanding of how structure forms and evolves. Modern cosmological simulations can reproduce the overall pattern of the cosmic web, starting from initial conditions derived from the cosmic microwave background and following the gravitational evolution of matter through billions of years of cosmic expansion. These simulations predict statistical properties of the structure, including the clustering of galaxies at different scales and the abundance of clusters as a function of mass, and observations test whether these predictions match what we actually observe in the real universe. Webb's contributions to this comparison include extending observations to higher redshifts where fewer measurements exist, and providing detailed characterization of high redshift clusters and their galaxy populations that constrain simulation parameters. The distribution of matter on these larger scales also provides constraints on the nature of dark energy, the mysterious component that drives the accelerating expansion of the universe, and represents approximately 68% of the total energy content of the cosmos, according to current estimates. Dark energy's influence on structure formation occurs because it affects the rate of cosmic expansion, which in turn determines how much time gravity has to pull matter together into structures at each epoch of cosmic history. If expansion accelerates more rapidly, structures have less time to grow and fewer massive clusters form, so the observed abundance and properties of clusters constrain the properties of dark energy that controls this expansion. Webb's observations of high redshift clusters contribute to these constraints, measuring structure at early times when theoretical predictions are most sensitive to cosmological parameters, and extending our leverage on these fundamental quantities that describe the overall nature of the universe. As we contemplate these largest structures, there is something both humbling and clarifying about recognizing the cosmic web that spans the observable universe, a pattern that extends far beyond anything we can directly experience, yet obeys the same physical laws that operate locally. The same gravity that holds you to Earth's surface and Earth in orbit around the Sun operates across hundreds of millions of light years to shape the distribution of galaxies and clusters throughout the cosmos. This universality of physical law is what makes cosmology possible as a science, allowing us to interpret observations of distant structures using principles established through local experiments and confirmed across the full range of accessible distances. The cosmic web is not random but deterministic, its pattern emerging naturally from physical processes that began with quantum fluctuations in the first moments after the Big Bang and evolved through gravity's patient work. As we reach the quiet conclusion of our journey through Webb's discoveries, it is worth reflecting on what this remarkable telescope represents, not just as a scientific instrument, but as an expression of humanity's persistent desire to understand the cosmos that surrounds us. The golden mirror that now orbits at Lagrange 2 represents the culmination of decades of planning, international cooperation, and technological innovation. Yet it also marks merely the beginning of a new chapter in our exploration of the universe through infrared eyes. Every observation Webb makes adds another piece to an immense puzzle that humanity has been assembling for centuries, gradually revealing the nature, history, and future of the cosmos we inhabit, with ever greater precision and depth. The discoveries we have explored tonight, from the earliest galaxies at cosmic dawn to the atmospheric compositions of distant worlds, represent only the first years of what promises to be a decades-long mission of revelation and understanding. Webb's fuel reserves, conserved by the precision of its launch, may allow it to operate for 20 years or more, providing time for systematic surveys, follow-up observations, and entirely new research programs that have not yet been conceived or proposed. Each year brings new observing cycles, with astronomers worldwide submitting proposals for telescope time, competing to use this extraordinary resource to answer questions ranging from the nature of dark matter to the potential for life on distant worlds. The telescope time is so precious that only a fraction of proposed observations can be conducted, making each approved program a carefully selected contribution to humanity's expanding knowledge of the cosmos. The scientific legacy of Webb will extend far beyond the individual discoveries it makes, influencing how future telescopes are designed and what questions the next generation of astronomers will consider most pressing to investigate with even more powerful instruments. Already, the success of Webb's deployment and operation has validated technologies that seemed risky when first proposed, including the segmented mirror design and the complex unfolding sequence that allowed such a large telescope to fit within a rocket fairing for launch. Future space telescopes will build upon these proven technologies, potentially creating even larger apertures that can peer deeper into space and further back in time than Webb's already impressive capabilities allow. The engineering lessons learned from Webb's development and deployment will inform space telescope design for decades, establishing new standards for what is possible when ambitious vision combines with careful engineering and international cooperation. Beyond the technical achievements, Webb has demonstrated the power of international collaboration in pursuing grand scientific objectives, bringing together expertise from NASA, the European Space Agency, and the Canadian Space Agency in a partnership spanning continents and decades. Scientists from dozens of nations participate in Webb observations and data analysis, sharing insights and building upon each other's work to advance collective understanding of the universe we all inhabit. This collaborative spirit extends to the public release of data, with observations becoming available to researchers worldwide after a proprietary period, ensuring that the telescope serves the global scientific community rather than any single nation or institution. The model of international cooperation that Webb represents offers hope for future large-scale scientific endeavors, demonstrating that humanity can work together effectively when united by shared curiosity about the natural world. The public engagement that Webb has generated represents another dimension of its impact, bringing cosmic wonders to audiences worldwide and inspiring a new generation to consider careers in science, technology, engineering, and mathematics fields. The images Webb produces are not merely scientific data, but works of natural art, compositions of light and color that reveal beauty in the cosmos while conveying profound scientific information. School children studying these images today may become the scientists who interpret future observations, continuing the chain of discovery that connects each generation to the next through shared wonder at the universe revealed. The accessibility of Webb's images and data through internet resources means that anyone with curiosity can explore the same observations that professional astronomers analyze, democratizing access to cosmic discovery in ways previous generations could not have imagined. As our understanding of the universe expands through Webb's observations, we also confront the vastness of what remains unknown, recognizing that each answered question tends to generate new mysteries, requiring further investigation and contemplation. The nature of dark matter and dark energy, which together comprise 95% of the universe's content, remains fundamentally mysterious, despite our ability to measure their effects on cosmic structure and expansion with increasing precision. The possibility of life elsewhere in the universe, while statistically probable given the vast number of planets, remains unconfirmed, though Webb's ability to analyze exoplanet atmospheres brings us closer to potentially detecting biosignatures in distant worlds. The ultimate fate of the universe, whether expansion will continue forever or eventually reverse, depends on properties of dark energy that remain poorly understood despite our best theoretical and observational efforts to comprehend them. Webb has also revealed that our theoretical models, while successful in many respects, require refinement to match observations, particularly regarding the early universe where galaxies appear to have formed faster and grown more massive than standard models predicted they should. These tensions between theory and observation are not failures, but opportunities for progress, pushing theorists to reconsider assumptions and develop more sophisticated models that better capture the complexity of cosmic evolution. The interplay between observation and theory drives scientific progress, with each constraining and informing the other, gradually converging toward a more complete and accurate understanding of how the universe operates across all scales. Webb's contributions to this ongoing dialogue between empirical observation and theoretical modeling will continue for years as its data is analyzed, reanalyzed, and interpreted through evolving theoretical frameworks that incorporate new insights. The philosophical implications of Webb's discoveries extend beyond pure science into questions about humanity's place in the cosmos, forcing us to confront both our cosmic insignificance and our remarkable ability to comprehend the universe despite our limitations. We are made of atoms forged in stellar cores, observing a universe billions of years old from a planet that has existed for only a third of cosmic history, yet capable of understanding physical laws that operate identically across all of space and time that we can observe. This cosmic perspective, reinforced by every Webb observation, provides context for human existence, reminding us that we are part of an immense, ongoing story that began long before Earth formed and will continue long after our Sun exhausts its fuel. The knowledge that we are connected to the cosmos through shared physical laws and common atomic heritage offers a profound sense of belonging, even as it emphasizes our temporary presence in an ancient universe. Looking ahead, Webb will continue its patient observations for years to come, methodically surveying selected regions of sky, monitoring variable objects for changes over time, and responding to unexpected discoveries that demand immediate attention and follow-up observation. Some of its most important discoveries may come from serendipity, objects, or phenomena noticed in the background of targeted observations, revealing themselves through careful analysis of data collected for entirely different purposes than their detection. The archive of Webb observations will remain valuable for decades, as new analysis techniques and theoretical insights allow researchers to extract additional information from data that has already been collected but not fully explored or understood. Future astronomers will mine this archive for insights we cannot anticipate today, finding patterns and connections that become apparent only with improved theoretical understanding or computational capabilities for data analysis. The technical performance of Webb has exceeded expectations in almost every measure, achieving better image quality and sensitivity than required, and demonstrating remarkable stability that enables observations previously thought impossible for a space telescope to achieve. The precise alignment of its mirror segments, maintained automatically through continuous small adjustments, produces images of such clarity that fine details in distant galaxies become visible for detailed study and analysis. The stability of its pointing allows for long exposures without image blur, accumulating faint light from the most distant objects, while its multiple instruments provide complementary views that together build a complete picture of astronomical phenomena. This technical excellence translates directly into scientific capability, enabling observations that push the boundaries of what we can detect and measure, extending our reach toward the fundamental limits imposed by the physics of light and cosmic expansion. As we prepare to conclude our journey through Webb's discoveries tonight, consider that everything we have explored represents only the beginning, the first chapters of what will become a vast volume of cosmic knowledge accumulated over the telescope's operational lifetime. New discoveries await in future observations, surprises that will challenge current understanding and open unexpected avenues of investigation, continuing the tradition of astronomical telescopes that have consistently revealed a universe stranger and more wonderful than previously imagined by theorists. The data flowing from Webb each day adds to humanity's growing comprehension of the cosmos, building toward a future where our understanding of the universe becomes ever more complete and profound through patient observation. Tonight's exploration has taken us from the launch of a golden mirror on a winter morning to the edge of observable space and time, examining galaxies that formed when the universe was young, stars being born in cosmic nurseries, and planets orbiting distant suns with diverse compositions. We have seen how Webb acts as a time machine, collecting ancient light that reveals cosmic history, and how its infrared vision penetrates dust clouds to reveal hidden structures that shape the universe on all scales. The journey continues tomorrow and for years to come as this remarkable instrument maintains its vigil at Lagrange 2, patiently gathering photons that have traveled across billions of years to reach its golden mirrors. Rest now with the knowledge that while you sleep, Webb continues its observations, its instruments collecting data that will become tomorrow's discoveries, adding to humanity's ever-growing understanding of the cosmos we inhabit and our place within its vast expanse.